Okay? So get prepared that you need coffee. Later on, you will have to encounter something very weird and very hard to understand. Okay? The hip. The hip is not difficult. Okay? So what is exactly the hip? Now the hip is a place that I will say that I will recreate another image of what malloc is for you guys. Okay? What is the meaning? The meaning is that what you learned from the last 2 years about malloc are all false. Okay? None of the lectures, even I teach year 1 student, I don't tell them what is the true meaning of malloc. Okay? So today I will tell you about what is the true meaning of malloc. And after you know the true meaning of malloc, okay, if you're really quest for performance, you will never use malloc again. Okay, just like one of my friends in an octopus, okay, octopus, the part, right? They tell me that they never use malloc call, okay, because they want you to have a very high performance. Okay, so what exactly is malloc? You already know that there is a place inside your process that will grow, that will change. It's called stack. Now it is another zone that will grow, it will stack, grow and change, and it is called a hip. Okay, it's called a hip. Now I already said that this diagram is not showing the scale. What's the meaning of not showing the scale? This area, how big it is? Approximately, depending on how large is the data segment. Say the data segment is normal, you never use a global variable, you have very few function call, then this area is more than, not more than, but close to 3 gigabytes. Okay, this area is called the 3 gigabyte wide. Okay, so which is a very wide area. Okay, and this area we usually call it hip. Now don't mix it up with Fibonacci hip. Don't mix it up with a priority queue. Don't mix it up with binary hip. It's none of them. Okay, it's just called hip. Okay, in Cantonese is 一堆嘢啦。OK， 普通话就是一堆什么啦哈。OK， English is a pile of things. Okay, so hip. So and a hip you already know how to assess that. Okay, to assess a hip, you only have 2 weapons, right? The weapon number 1 is created, called malloc. Weapon number 2 is free. I highlight them, okay? And I think this is the image that you get from your C courses, data structure courses, or other kind of books. They always tell you about this, okay? Which is wrong. Totally wrong. Because malloc doesn't mean that it's always give you new memory. It may give you something old. Free, never free memory. It sometimes don't free any memory. It sometimes just put your so-called free memory, put it aside. And if you are naughty enough writing a bad programs, okay, you already have one experience is that if I free the memory, I can still access to it. Yeah, some people, yes, okay, they experience that. You free the memory, you can still read and write it. Sometimes, not always. Now today I will tell you why and when you can do it. Okay? So that's why I said that it's very hard to understand unless you go to the OS course. Why sometimes you have segmentation fault? Some people tell you that, yeah, I call malloc or only malloc for 1 byte, but eventually I have a huge piece of memory and I go out of bound, no problem. Now I will tell you why. Okay? And this is 2 weapon, and the 2 weapon basically is to open up a new area of memory for you to use. This is originally we have a heap, and I said that the heap is for malloc. If you never call malloc, it will be empty. Now, but remember one thing. It is not always true that in the beginning of your code, okay, it is empty. Because why? There are so many naughty library code call malloc for you. Okay, the very famous example is fopen. Fopen silently call malloc without your permission. Okay, so in this figure, I will only show that you never call something special, mysterious. You just start with the main and then do your initialization of the variable, and you kind of want to have malloc create new memory for you. And what is malloc? Malloc will eventually call a system call. Okay, how to pronounce it? Okay, don't call it bark. Okay, it's not a dog. Okay, we usually call it break. Okay, this system call is called break. Why is it called break? Because it means there is a line that this system call will draw over the memory, and this is called breakpoint. Below that breakpoint, the memory is for you. Okay, go beyond that breakpoint, your program will break. Okay, what is that? Because you access memory that you didn't create it, of course, segmentation fault. Okay, so this is what I invented. Okay, how to remember name called break. Okay, it will break if you enter the zone. Now this break, what is the use? Malloc will grow the area, and what is free? Free will shrink the area. Okay, so they are a pair of our eventually called a system called pair. They are all called break. Okay, but the break will control whether to grow or to shrink. Okay. So now you know what malloc and free is. It's just to control how big this area is. And why you need malloc and free? Because malloc and free is what we call a control system or control library to control how to make use of this area. Okay? Now I will show you what malloc is. Okay? Now this is the program. This is the program. And I use two pointers called malloc twice. Okay? Each of the malloc call are very small items, right? 16 bytes. Okay? I don't know why 16 bytes. Maybe you create a structure containing 4 integers, so add together 16 bytes. Okay? Or I just really want 16 bytes. That's all. Okay? And you already know that the malloc call is addressed by bytes, right? Okay? So it's it is decoupled from the pointer that you point to. Okay? So you use a char pointer to receive it. It doesn't mean that you create 16 char. It's just 16 bytes. If you use an integer pointer to point to it, receive the new address, it doesn't mean that you create 16 integers. Okay? Now, that means that if I do one very special things, I don't know whether to try it or not. Call malloc twice, receive 2 pointers, and do pointer subtraction here. Do you know what is that? Do you know what is the value that you have received from malloc? Do you know what is that? You never inspect it. It is an address, a memory address. Okay? So the return value is a memory address, and that's why we call it a pointer. And what is the meaning of I do a subtraction over that? It means I do a memory address subtraction. Okay? So let's say one call is 1234, and another address call that received by from this malloc call is 24XX. Okay? Then you do decrements. Then you will know the distance between the two malloc calls. Okay? So by using illustration, a very easy thing that you create one guy here, you create 16 bytes. But as a matter of fact, using malloc call is not that easy to understand. I guess while Calvin, our tutor, tell you about the secret about malloc, is he already said that there is some control structure that control malloc. Okay? Now before I continue with this animation, I first show you the answer. Okay? So the program is called, oh, I didn't create this, malloc distance. Okay? So I show you the program. So I create even one more in the program, 3 blocks of 16 bytes. And I measure the distance between 2 and 1 and 3 and 2. Okay? Now, first of all, understand one property. The later the malloc call, the bigger the address will be. Okay? Because why? Because of this control. Once you call a malloc, the break point will grow. You call another one, the breakpoint will grow again. Okay? So that's why I said that when you call malloc call, the later call will usually get a bigger address. And that's why I expect this will give me a positive number. This will also give me a positive number. Okay? So what is the distance? The distance is not 16 bytes. The first malloc call and the second malloc call, okay? Suppose they return you the starting address of that memory block. And because these two malloc call is adjacent, suppose they are stick together, but no. You have 8 free bytes. You have 8 more bytes that created for you. And what is that 8 more bytes? What is that? It's this block. This deep red block. You create one more block, okay? You will create another control structure, okay? And that control structure is created by malloc call, not for you. Not for you. So that's why every year one course or other C language course tell you one very important thing. When you ask for 16 bytes, don't play with the 12 bytes, oh no, the 20 bytes. Okay, don't play with bytes beyond your allocation, because the bytes beyond our allocation is very important. They are control structure created by malloc, and as a matter of fact, if you disobey this, don't obey with the 16 byte malloc restriction, you call for malloc call of 16 byte, you continue to write things, you will override the later malloc call. Okay? So I see many people, and I see many people not from your class, okay? From my previous, while I was a tutor, many people send me codes for the bug, okay? And they usually present one very strange fact to me that they say that their program is crazy. How crazy it is? I do a for loop, and that for loop will change every memory that I have. Okay, and because their for loop is go way beyond their malloc area, so they will change other memory, and it create troubles in your program. Okay, and this is the result. Okay, but why malloc create something extra? Why it don't just remove this guy, yeah, be environmental friendly, right? Because you create 8 more bytes. Now, what is that 8 more bytes? It is being used later by the free call. Okay, this actually what I said. This is actually a linked list. A linked list to link together all the free blocks. Now, I don't have free blocks yet. All blocks are created and will be used later. And let's say I want to free something. Okay, let's say I create this long chain of a malloc area. I want to free a particular one. Okay, so let's say this is the pointer I received from the malloc call, and you know that you always need to free a piece of memory, okay, with the pointer received by the malloc call, plug into the free. And now you know why. Because here you point to this location, you start with the free, then by using some magic, we can locate the control structure just before the malloc block. If you don't do so, you just, let's say I point to this location, okay, I don't know why I point to this location, and try to call free, then it will go crazy. Okay, so now I call free, what will be the result? There will be 2 kinds of results. One, this is the old heap, you call free. The version number 1 is, because this is the last block, this is the last block, so the system is very clever. I mean, not the system, the one who write malloc and free. Know that this is the last block because you cannot find a later control structure. So why not we shrink it? We move it, return that to the system. And the meaning of return to the system means that if you access something beyond this, segmentation points. Okay? This is not the end. How about case 2? Case 2 is, let's say we free this guy. Let's say we free this guy. But we blindly follow what I just said. Okay? Oh, when I'm free, I will shrink the area. Okay? Let's do this. Shrink. Okay? Goodbye to this guy. Okay, you will destroy something that preoccupied there. Okay. So what will be the results? Now this is the results that I tell you. Free may or may not return memory to the system. And this is the case that we cannot return memory to the system. And how malloc will treat this, okay? Don't tell me that there is no management. There is a management. And the management block is, I simplify this, okay? The true management structure is very complex, okay? They are crazy, using 8 bytes and create very crazy structure. Now this is my version. I just simplified it, and I treat this as a linked list. And what is the two field? I just need 8 bytes. One is to represent whether you are a part of the linked list. If you are as a part of the linked list, it will be non-null. If it's not a part of the linked list, I will set to the null. Later on, you will see how I create the linked list. And here is the size. It's the size of that malloc block. Okay, so here it's called 16 byte. So I know that there is 16 hiding here. Now, I know that I want to free the middle one. Very easy. How to do it? Basically, there is a global variable. This global variable hiding inside the C library. Okay, let's call it a heap. Okay, a global variable called heap. Okay, originally it's a null to represent that there is no free block. And then use this as a pointer pointing to this location. Okay, and then this location now can be accessed by the global free list. Global free list. And this global free list will eventually point to null. So that I defeat what I just said. Okay, this null may or may not represent a free block. Okay, but by following this linked list, I know that this block, so I color it into gray, is free. Okay, so this is how malloc don't return memory to the system. Okay, and that's why somehow you call free, and your program has some bug. You can still access that piece of memory because it's still here. It's still inside your program, inside your process. Any problem? Any problem you want to ask? Yeah, very easy. Very easy, just a construction of a linked list. Now, how to expand this linked list? Yeah, let's say I'm crazy. I do a alternating free. Okay, I free this, alternating, this guy, this guy, this guy. Okay, the order is this, okay, from the left to the right. And then I will create this linked list like this. So you can see a plain block, and then gray block, plain block, gray block, so and so forth. Okay, this is the construction of the linked list. And this pointer field will be pointing the start of the next console structure. Now, why we need the free list? We can forget about the free list, right? I just put the memory there. Yeah, I know that it is free, okay, but I cannot really free this, so put it there, okay? Because, well, let's say what is your program is doing. Your program is doing something like this. Malloc 1 million times, and free, I don't know why. You free 1 million minus 1 time, but without the last block. Okay? So what will happen? Okay, you will have to create a chain of free memory, but the last block is not free, so you cannot change the memory. Okay? Then you do it again. You malloc 1 million times again. Okay? And continue the process. Eventually, what will happen? Do you know? Do you know what will happen? Out of memory. You use up all the memory. Okay? But you have call free. Right? You have call free, but why it doesn't return to the system? Because you do something like this. Okay? You are doing something like this. So you will eventually create trouble in your program, and we usually call this, if you don't care about this, okay, a form of memory leakage. This is a form of memory leakage. So that's why the system will maintain this free list for you and hope that eventually you will use it again. And how to allow you to use it again? Very simple. Very simple is that later on I will go back a few 2 slides. Is after you malloc, you call free, you call malloc again. Okay? Let's say I have this free list, okay? And this free list is already created. Now I want to call malloc again. Now the system will do something like this, very easy. To look for a hole that can satisfy your need. Wow. Easier. Let's say, very unfortunately, okay, this is an unfortunate case. I ask for 32 bytes. Okay? Now inside this list, sorry, I cannot give you 32 bytes within this list. Every block is 16. So we need to create new memory for you in this case. Now what if I have a not so big malloc? Let's say I malloc for 16 bytes only. So happen that, very lucky, the first guy already has 16 bytes in the original list. Original list is like this. The first block is 16. So I will create this as if I create, okay? As if I create this block for you, and as a matter of fact, I'm not creating this block for you. I recycle it. Okay? This is a form of recycle of the memory that originally is free. Okay? Any question you want to ask? So this is a malloc. This is the truth of malloc. Yes? Where is the linked list is stored? Okay? The head of the linked list is here. Is a global variable inside the C library. And the linked list, of course, is already in the heap. When you call malloc, the structure is already there for you. Okay? And when you free it, then you will use the structure. Okay? Yes?
What if we have some adjacent memory that has been free, but we want to malloc a memory that is smaller than
We will merge that. Later I will talk about it. We will merge the adjacent free blocks. Okay? So, go back to the slide that I skipped. They're very easy. It's about the free call hazard. Okay? What is the hazard? The hazard is you need to always free by pointing to the exact location of the pointer. I've told you now. I have a figure. What if you point here to ask for a free? Okay? This is always puzzling me while I was a junior programmer. I was a first-year student. I know that this is a piece of memory that I create. Why I can't point to a particular location, let's say the middle location, and ask for malloc memory to be free? Now I know, because the calculation is very, very easy. You give me this pointer, okay, I believe in the programmer, I'm the malloc library. I believe in the programmer, and the programmer tells me that this is a pointer. I immediately cast the memory as a structure of this linked list. And then go back one slot. Then we'll treat this area will become a free zone. Then what will happen next? 99% segmentation fault. Okay? Because here is something that crazy, right? Something that guides you to believe that this is a huge memory, maybe so happening store 1 million, a number 1 million there. So you will believe in the number and try to, it's 1 million, it's way beyond the break, so why not free it? And then you will caught some big error. Okay? So the problem is, there is some implementation problem here. What is the implementation problem here? No one asked me these questions. I choose to reallocate, I should say, the first guy. Okay? No one asked me why it is the first guy. Why don't we take the last guy, right? We can take the last guy. Why always first? Okay? Or are you going to scan the list so that we can find the best one? Yeah, there are different strategy. And what we call here, we call a memory allocator. Okay? During its evolution, we have different versions. Okay? Some will implement strategical first fit. Okay? Find the first that just fit or big enough, then use it. Some will use the last fit, okay? Try to malloc here, okay? And some will scan the entire list, okay, and do other purpose and try to have a better use of the free memory, okay? So this is out of our scope because why? We don't have any exercise for it. We don't have any assignment for it. I can't remember which year. Maybe approximately 3 years ago, we still have this assignment. Okay, ask you to pretend to be a implementation of a fake malloc and fake free. Then I will send you some programs to plug in your fake malloc and fake free. I will drive your call and see whether your memory can be used, whether your memory is correct, whether I use your library will get segmentation fault or so on and so forth. Okay, so we will skip still subtle cases, okay, because we don't have assignments. Now I have some issue for you. I don't know whether you have tried or not. How many of you have tried bar1 malloc? No one. No one. Why? Why don't you try that? Okay, it won't explode. Yeah. The worst case is to reboot the system, right? Why don't you try that? Okay. So what is the meaning of malloc? You know, is to change the breakpoint. Now, what if the breakpoint has no space to grow? Right? The breakpoint can grow, but I say that the maximum amount of memory that you can grow is approximately 3 GB. You don't have memory to grow, then we will have a very famous error called OOM error. Yeah, you can already QE or using a Google, you can look for it. Become OOM, then you will find a lot of articles talking about OOM. Yeah, this is called OOM error, all of memory error. So, anybody dare to try this? Do you know what is it? How many of you don't know what it is? Will the program stop? Tell me, will the program reach return 0? And if reach return 0, why? I can discuss your neighbor, right? I'll wait for an answer. Where it stop? I give you 30 more seconds. Yeah, if you have a laptop here, you can try it out. No problem. The worst case is in reboot, right? And reboot normally, okay, not reboot unexpected. Okay, let's do a very simple folks. Who think that it will stop? Only a few. Only a few. Who think that it won't stop? Who think that your computer will stop? Okay, no one. Very good. Okay? So why it stopped? Because of a break, right? There's a break to break out of the bar1 loop. But will the break will driven normally, and why it's being driven? This is something that your junior teacher tell you about malloc, or some tutors tell you about malloc. They usually tell you to do one thing, but you never do it. The thing is to check the return value of malloc, whether it's null or not. And after you are being cheated several times, yeah, they tell you to check, okay? And you never check, no problem, okay? I already have 10 years of the programming experience that never check the return value. Yeah. So you don't check it. Now I will show you why we need to check it, okay? You can see this version here, version 1. So that means that I have many versions. Okay, so a very small modification here. What is the modification? I don't let the process dies. I just let it to break it out, And also I plug in p error so that I can see the system error message, what the system think about this. If I get the pointer equal to null. Okay, and after I break it, I put a pause here so that you can take a look at the process using its PID. Okay? So let's go. No problem, huh? Now I run it. Guess how many times I need? Within 1 second. Can you see that? What is the error message that's being produced? Malloc cannot allocate memory. Yeah, I guess this is your first time to say it. Okay? And now, believe me now, you need to check. Okay? And what's the results? Around 3G. 3 gigabyte is how much? wait. Yeah, I'm bad. Okay? Oh, 3G, 1024 times 3. Oh, okay. 3072. Okay? Yeah, I need to run it again. I'll run it again, okay? So it's very close, right? I just have around 20 megabytes that cannot malloc. Usually 20 megabytes, including, let's say the stack. You have the stack, you have the code, you have the global variable, you have the library that loads into your process. Okay? So just a little bit things get lost. You cannot allocate. But now you can see this, I can allocate as many memory as possible. Now I put a hold on the process. Why? Because I want to check something. 31304. Whether this memory are really allocated, right? I use only 1 second to create a process allocating 3 gigabytes. Do you believe in it? Let's check. Okay, suspend it. I just suspended it, not being killed. Take a look. Take a look. The process is still alive because I just suspended it. And after I take a look at the process using top, you can see this. What is the column? You can remember this column, right? Because I just said once in I don't know which lecture. Okay, it's called virtual memory allocation. The virtual memory allocation is really close to 3G. Okay, 3 gigabyte allocation is done, and that means what? That means those memory are really given to your process. But I also explained to you of these two blocks, right? These two columns, and this column we said. Give a name for it. We call it resident memory, the memory that really reside on the memory, the RAM. So that means that what I'm doing is just a hollow malloc. The malloc just give you false hope. Okay? What is false hope? You don't have 3G of memory. But what are the RAM really on the physical RAM? The memory on physical RAM is only 12 megabytes. Where are the remaining things? Later on, I will guide you how to get it. Okay? You cannot see this. I bring my small laptop here because I don't want to demonstrate now. I'll demonstrate really use up this portion, okay, in a class. Okay? Yeah, that will be very horrible. I don't want to call this in my Mac machine. Okay? Yeah. And you can try. Yeah, the worst case is reboot. Now, I have version 1. That means that I will have version 2. What is version 2? Okay, version 2 is to show you one thing. The thing is, where is my big map? Big map, oh, where? Oh, here. The big map is here. The big map, this is the big map. I want to show you the big map here. All components act together is a constant. I cannot suddenly get more memory. Let's say I want to expand the global variable zone. After I expand the global, can I still get 3G of heap memory? Okay, this is what I have for version 2. Let's see here. Inside version 2, what are the changes? I have 2 changes. First, I expand the stack. Okay, you know the stack only have an 8 megabyte. I just push it to close the limit, okay, close the limit here, I also expand the global variable, okay? So I have more LK being allocated before I call any malloc. Now, how about the malloc? Will the malloc being changed or being affected? Let's see. Didn't kill it. Very horrible. Forgot to kill it. Okay. Version 2. Version 2. So no problem. I have the local variable. I have the global variable. Okay, one is 1G, global variable is 1G, and the local variable is close to 8 megabyte. Run. Okay, it's just complaint. Okay, but don't afraid of the complaint because I already have a minus big O 0. It means no optimization, so that area of memory won't be optimized away. Okay, now I run. And version 2, go. Can you see that? I get fewer from malloc. So what is the implication? The implication is that the whole big map here, I have several components. The components add together is a constant. Okay? You have more global variable, then you cannot malloc so many memory, and vice versa. Okay? And I have skipped a page. And that page is to tell you still about this limit. The limit is 3 GB for 32-bit system. 32-bit system will reserve 1 GB to the kernel. You only can, for each process, use 3 GB, not 4. Okay? So here are the programs that I can prove to you this is the limit. Now, the last program, version 3. I don't have any code here because I don't want to run it now. Horrible, okay? So I will wait until the backup class, okay? Because I need to set up, I need to take some time. And what is the difference between version 1 and version 2 and version 3? The version 3 had one more statement. One more statement, and the statement is highlighted here. Memory set. Per malloc call, I will set zeros to the block that I have created. And this is a true OOM. You will see the entire system getting slower and slower and slower and suddenly stop. And suddenly nothing happened, just like nothing happened because the big eater is being killed. Okay, by the kernel. The kernel find that, oh, you take up so many memory, I kill you. Okay? So later I will explain to you the running of this program. I don't want to run it now. Okay, if you try to, first of all, don't run this program on any public computer. Okay. You see, I didn't call any system call, right? Any special system call. So that means that you don't need any special privilege. Every people can run it. Okay. Don't try to kill other people processing. Oh, there is a malloc. Okay, there is no malloc. There is a malloc. There is a professor running a malloc. It should be a memory big eater. Then I try to call this. Try to kill him. Okay? I will say that it's possible. It's possible. Why? Because the kernel may think that he is more he is more naughty than your program. Okay? I don't know how the kernel judge it. Okay? Because why? I already tried something. Some years before, people asked me to try running 2 instances of this program. Which will be killed? Random. Sometimes it's the first guy, sometimes it's the second guy. Okay? Then how about the malloc? Okay? Don't run in a proper computer. Okay? Of course, another warning is don't run on 64-bit computer. Did you call you understand that? No. Did you call back MVM set? Is it being killed? No? Killed. Okay, it's being killed. Okay, it's good. Okay? Don't run in 64-bit system. Do you know why? Because 16-bit system don't have this 3 GB barrier to stop you. What will be the result? You have a MacBook, 16 GB. Take out 16 GB. Okay. You have turned on what we call the swap. Take out memory from the swap. Okay, and continue to take whatever memory they can take until the kernel finds it ID to kill him. Okay, but you have memory RAM, right? You have memory. You buy the MacBook Pro 16 GB. So you will take many memory, and after that it has been killed, okay, you will have a disaster. Later I will tell you what is a disaster. Okay, the disaster is written in a part 2 of this chapter. Very horrible. I tried once. I regret. Okay, segmentation faults. What exactly means the meaning of a segmentation fault? Okay, you already experienced it. Okay, raise up your hand who didn't experience it. I buy you a coffee. Everybody have tried it, right? Okay. So this is something that someone will tell you. Let's say you are in I don't know which course. Maybe a year 1, you take some C course. Maybe your data structure course. The first time you see segmentation fault, just like now I'm teaching the year 1 C programming, the ENGG 110. When they first see segmentation fault, they don't know what it is. Then we will come up with a very interesting idea to explain it. Okay. The idea we need to be, we cannot tell lies, right? We're a teacher. But we can tell the truth also. Because the truth needs operating system concept. So then we come up with this statement. When you're assessing a piece of memory that not belong to you, then you will get segmentation fault. Did I say anything useful? Can I help you to debug? When you see it, oh, thank you. Then how to debug? Now I will tell you how to generate segmentation fault. Okay? How to generate segmentation. You know how to generate, then you know how to debug. Okay? So, what is generation? The generation is like this. Basically, inside a CPU, what is the truth about the memory? It's like this. Now, on your left, it's my original big map that you find, right? There's a big map that you find. And Intel-based CPU, how Intel-based CPU will map this map into their physical memory is like this. Okay? Usually there is no gap between code constant and with the data. After data, there is usually no gap between BSS and data. No gaps after BSS and Heap. Unless you never call out, then you won't have this allocated heap block, but always an allocated sum. Okay? And here, allocated stack. Okay? And this area will be shared by the stack and the heap, and they will grow together. Now, what are the remaining parts that I never explained to you? This part and this part. These two parts are reserved. When you touch them, segmentation faults. Don't make a read and write. Okay? Don't make a read and write. Now, think about it like this. I have a random address. Okay? I don't know what is this address. Usually, your segmentation fault is generated in this way. I have a random number. The random number inside the pointer. Then I'll dereference it. Now, when you dereference it, the trick comes. Which area after I dereference is fall into? Okay? If it so happens that you dereference it, it's fall into this area, no problem, no segmentation fault. If that random number fall into this area, segmentation fault. And if the address fall into this location, what is that? Null. This is null. Segmentation fault. Now I give you a map. A map why we have segmentation faults. Okay, this is a very useful map for you to remember in your brain. Not in an examination, of course. I don't come up with a previous slides and remove all the yes, no, and ask you to fill in it. Okay, it's crazy. Okay, are you honest? Okay, so what is that? we have two columns. One column is an operation for read. What is the operation for read? Is you have this random pointer, you dereference it. After dereference, by the way, how many of you don't know what is dereference? Okay, thank you. Dereference it, then you try to read the content. Another is write. You dereference it, and you try to treat it as a variable to save data in. And the segmentation force allocation will be like this. You see, what's yes, what's no, of course. Yes means I have segmentation force. No means I don't have segmentation force. So for the yes part, okay, yes means that yes, segmentation force, okay. Then here, right, the right part we have more. Because the right part, you can compare, right? The code and the constant, okay, occupied a read-only data range. So when you write to it, segmentation false. Or you try to read and write over this unallocated zone, segmentation false. Now, try your luck. I have a random number. Put it in. Will I have segmentation false? Usually you will have. Because I said that I didn't draw to scale. This area, if you don't have too much memory inside data, not too much memory instead, no, never comment out. Here will be 3 GB. Why very wide zone? Then you come up with a random number, usually we'll get segmentation false. Okay? And now, how many of you don't understand this? Okay? How many of you need some time to digest the yes, no? Maybe I give you a break. Okay? During the break, I'll keep showing the slides. Okay? And after the break,